Hi, everybody. Thank you all for coming. This is the Wilderness Issues Lecture Series, a series that has been running through the University of Montana by the Wilderness Institute for the last 30 years. Our theme changes every year. This year we chose to focus on conservation in a time of climate change. My name is Nikki Fear, and I am the coordinator of UM's new Climate Change Studies program. I am one of the series coordinators along with Lori Young, who's been running in and out of here. She's the director of the Wilderness Institute. The two of us, the Climate Change Studies program and the Wilderness Institute, are the co-sponsors for this series. And we have been able to put it on through a grant from the Cinnabar Foundation. And I want to thank the ED who's here, Steve Thompson, and the board chair is Robin Tawny Nichols. And the Cinnabar Foundation has been a great supporter of conservation and education in Montana and the greater Yellowstone for many years. Probably almost all the conservation groups that you could imagine have received funding support from Cinnabar, like Montana Trout Unlimited, Montana Wildlife Federation, Clark Fork Coalition, Wildland CPR, and so on and so on. So thank you for your work with the groups and with us here tonight. We also got a generous donation by Rick and Susie Gratz, who donated the use of their artwork for our series poster and also for our weekly flyers. So tonight, our keynote lecturer for this series is Dr. Rob Jackson. He comes from Duke University, and he's going to be speaking about global change, tipping points for people, and the biosphere. We'll introduce him soon, but I just want to say a few more words before we hand it over to him. We do hope you return next week. Our speaker is going to be Joel Berger. He's a professor here at the university, teaches about wildlife conservation, has a lot of experience doing conservation work around the world. He's going to be speaking about ice, wildlife, and us, what legacies, what lessons. The series in total involves 8 speakers each Tuesday night through February and March. Speakers after Joel will include Sarah Bates to talk about water policy in a warming West. We'll have people talking about forest management, given our fires are tending to be longer and more intense. We'll be hearing from someone to talk about bark beetles and community resilience. We'll be hearing from someone talking about how to deal with the increasing costs of protecting homes in the wildland interface. And then we'll end the series with a talk about how to build resilience and steward nature through climate change. So we hope you come back each Tuesday night for that. And I'm going to pass the introduction off to Corey Cleveland, who had the bright idea to invite Rob Jackson here to speak with us. Corey is an assistant professor here at the university in the Department of Ecosystem and Conservation Sciences, and he is an ecosystem scientist. So thank you, Corey.
So it's a real pleasure to welcome Rob Jackson here tonight. And when I was thinking about preparing this introduction, a couple of things became both immediately and abundantly obvious. The first is that in order to give you even a remotely comprehensive list of his accomplishments was going to take us till 8:30. So I'm not even going to try and do that. But even the annotated version is more than I could remember at this point. So I have a cheat sheet here. So bear with me. So Rob is a professor of biology and director of the Center on Global Change at Duke University. And in a nutshell, he and his group do applied work on water, carbon, nutrient cycling, plant and microbial ecology, and global change. And in particular, climate change is at a real piece of that, and the effects of people on the planet. And I think that's a really interesting and gives you a broad sense of what Rob is working on. In his own words, the goal of his research is to build predictive scientific frameworks that help guide policy solutions for global warming and other environmental problems. And I think that's what's really unique about Rob, is that solutions are at the heart of what he and his group are trying to do. In the quest for solutions, he directs the Department of Energy's funded National Institute for Climate Change Research for the southeastern United States, and co-directs the Climate Change Policy Partnership, who's working with energy and utility companies to find practical strategies to this problem that we're all facing right now. Rob has lots of degrees in chemical engineering from Rice University, master's in ecology and statistics from Utah State, and a PhD in ecology from Utah State as well. And he's been the recipient of a number of really prestigious and tremendous awards. The Murray F. Buell Award, that's awarded by the Ecological Society of America. Rob was awarded at NSF. Sorry, at NSF. Early Career Scientist Award, and I'll spare you a lot of the details. It goes on and on. Beyond his amazing contributions to the field of science, he's got hundreds of publications, or 150 publications. He also has been an author of some popular books. This is one, The Earth Remains Forever, and a couple of interesting children's books. So the first one, Animal Mischief, and for those of you who've been waiting impatiently for the sequel, Weekend Mischief is now available. So the title of Rob's talk tonight, again, Global Change Tipping Points for People in the Biosphere. So please join me in giving a warm welcome to Rob to cold, snowy Missoula.
Thanks. Well, first of all, thank you for the invitation. Corey, Nikki, thanks to the Cinnabar Foundation, Steve and Robin. Thank you for being here. I see people in shorts here. It's a warming world. It's actually hard to give a climate talk. You know, it's minus 10 degrees. I landed in Denver today coming from the West Coast. It was minus 11 on the runway. I thought this was going to be a tough sell today. But so I want to talk about, I'm going to talk a little bit about climate change, but I want to, the series is about climate change and conservation. So I'm going to talk a little bit about, very briefly, some evidence for climate change. But I'm going to get out of even my comfort zone pretty quickly here. So I want us to think a little bit about what happens if we don't do something about climate change. What if we don't act to change the way we generate energy, or don't act to alter what we consume, or don't think seriously about how many people we want to put on the planet? What are some of the options that might be at our disposal that we might be forced to take, or at least to think about? And what are some benefits, some pluses and minuses to those? And so that's what I really want us to think about. And tipping point's obviously a nod to Malcolm Gladwell's book, Tipping Point, the idea of being sort of a threshold, a nonlinearity, a step change in something that places us in a new state or a new position. So that's where we're heading today. We'll spend about the first 10 minutes reviewing very briefly climate change itself. But let's step back. This series really is about conservation and climate change. And so I think the basic entry point is our population and consumption issues. Fundamentally, population, that intersection between population and consumption, drive all of the problems that we study when we're thinking about the environment. Some more population related, some more consumption related. This is for those of you who haven't read Joel Cohen's book, How Many People Can the Earth Support? This is about a decade old. This is a wonderful book, just laying out everything from the history of estimates of carrying capacity for the Earth to the different limitations, perhaps, in how many people the Earth support, and lots of things that we just simply don't know. So I would recommend this book highly. So let's start with the first tipping point, and that's how many people will there be? And this is not news to anybody in this room, but there's an enormous range of people on the planet, depending on what scenario happens, by the year 2050. So these are estimates from the United Nations. You have to bear in mind for the young students in the room that around the time when my parents were born, there were just about 2 billion people on the planet. And now we put 1 billion people on the planet every dozen or so years. Still, even though the rate of population growth has slowed by about half from its peak level, there are now more people on the planet. So about 75 to 80 million more mouths to feed, people to clothe, and provide a quality of life for. And essentially, which of these scenarios we end up just in the next 40 years has a huge effect on the environment. So I was going to say this is the first tipping point, really. How many people will there be? The middle of the road estimates from the United Nations are in the neighborhood of 9 to 10 billion, excuse me, here. Today we're about 6.9 billion, inching up to 7 billion about 2010 here. So pretty soon we'll start diverging and figuring out where we end up, barring catastrophe, which no one wants. We're not going to peak at 8 billion, that's clear already. But is it going to be, will it be 9 billion, 11 billion, 13 billion? And by 2100, there could be 15 billion or more people on the planet, with enormous consequences for habitat and such. So the number of people clearly matter. But what we consume clearly matters too, and it's obviously about total consumption, about per capita consumption. This is a 50-year record of carbon dioxide emissions, and there are two lines on this figure. One that you see is the increase in fossil fuel emissions, so these are billions of tons of carbon, if you will, on the y-axis here. So this is the growth in the fossil fuel term going back to 1960, about the time that I was born, about 2.5 billion tons a year. Now about 9 billion tons per year of emissions. That's carbon, about 30 billion tons, 35 billion tons of carbon dioxide. And this is the other important term in this balance, important ecologically from a biodiversity standpoint. That's the net term attributable to deforestation, for instance, loss of carbon from the soil due to agricultural conversion and things like that. So that term has stayed approximately the same. I would argue, and I'm going to talk about solutions and successes tonight as we go through some of the problems too. This so far is a real success. The rate in deforestation, tropical deforestation in particular, has decreased substantially in the last decade, in large part due to efforts by Brazil. All right, so we're now down about still a billion tons of carbon, about 3 or 4 billion tons of carbon dioxide a year. But the bulk of the problem is now the fossil fuel term. Okay, let me insult your intelligence just for a minute. We'll spend about 5 minutes going through the history of greenhouse gases. What is a greenhouse gas? Greenhouse gas is a gas that essentially delays the passage of long-wave radiation back out into space. So here, this yellow line is sunlight reaching the Earth's surface. Some of that sunlight is reflected back into space. Some of it's absorbed by plants in photosynthesis. But everything on the planet, our bodies, the floor of this room, the sky, rocks emit long-wave radiation as a function of the temperature, the fourth power of our temperature. And it's that long-wave radiation that, of course, the greenhouse gases delay the passage of, or trap, if you will. And without greenhouse gases, as you all know, the Earth would be a frozen ball of ice and we wouldn't be here. So they're fundamentally a good thing. But as we've increased the number, the concentration of these gases, we've increased the trapping ability, again, if you will, of the long-wave budget, raising the Earth's temperature. A brief history that most of you know. A lot of controversy in the media. Is it real? What do we know? What we don't know? The basic physics of global warming and greenhouse gases was worked out in the 1800s. Okay, 1820s, Jean-Baptiste Fourier was the first person to describe greenhouse gases. He used the term, the analogy of a greenhouse for that. Some of you taking physics or chemistry now know him from a Fourier transform in your class. The 1890s, several people had already made the link intellectually between greenhouse gas concentrations, warming of the Earth. If we were, through human activity, to increase the concentration of those greenhouse gases, we're likely to warm the Earth further. Didn't suggest at the time that it would be a problem or anything like that, just made that connection between fundamental concentrations of those gases and the Earth's temperature. And then in the 1950s, Dave Keeling, we often talk about, he was the first person to monitor carbon dioxide concentrations in real time all the time. And it's the famous Mauna Loa trace that he initiated that I will not show you, which you've all seen 100 times. I will show you an older version, though. Long before the Keeling trace, which goes back 50 years, as Earth scientists, we want to know the long-term history of the Earth. And 5,000 years, 500,000 years if you're a geologist isn't really long-term. But it's a pretty remarkable time machine of a record through going back from present day in time through the Vostok ice core record, the Greenland record, different ice records. So what is this record I'm talking about? These are layers of ice laid down annually, the trap bubbles of gas that allow us through coring to go back and actually literally look at what the atmosphere was like at that time. There's no proxy involved or anything else. It's actual samples of the gas from that time, going back now close to 1 million years. So that's a record of almost 500,000 years with carbon dioxide concentrations on the y-axis. You see the cycles that are the ice ages that you're all familiar with. When carbon dioxide concentrations are low, we're deep in an ice age. We come out of an ice age very abruptly in some cases for reasons that nobody completely understands. We're in a warm interglacial period. We go back into an ice age 10, 20,000 years ago. We started out of the last one. And then something else happened. The Industrial Revolution happened, and now we're today up at about this concentration, 390 parts per million or so. Okay, the next tipping point, where are we heading in 2050 and 2100? The best efforts today talk about stabilizing carbon dioxide concentrations at 450 parts per million. Best estimates from the models are that that would give us a warming of about 3 or 4 degrees Fahrenheit, 2 degrees centigrade. I'm an optimist at heart, or I wouldn't work on climate change. Very, very unlikely, I hate to say it, very, very unlikely that we're going to make that, 450 parts per million, because of the lack of action so far and the growth of industry in other parts of the world. There's essentially a coal plant coming on almost every week in China, and their per capita emissions are still well below ours. So, really we need to be thinking about, can we stabilize concentrations here in the 500, 550 range? It's possible that in a worst case scenario for some of you students in the room that we could be at the top of that graph in your lifetime, which is not somewhere that we want to be. And of course the world doesn't end in 2050 or 2100. These processes keep going. So on that happy note, these are a couple of old magazine covers. One, Time magazine on the left, The Heat is On, How the Earth's Climate is Changing, Why the Ozone Hole is Growing. This was at a time when the ozone hole had been discovered, efforts towards the Montreal Protocol, one of the most remarkable environmental success stories in the world was going on. But already 25 years ago almost, this discussion was current in the popular press. On the right, my favorite news magazine, The Economist, staying cool about our changing climate. Just a slide or two on evidence for climate change. There are reams of data, satellite data, buoy data, borehole data, weather stations, you name it. There is a rich, rich set of data that all points to the Earth warming. So I'm just going to work from the premise tonight. Climate change is real. The vast majority of it is caused by human activity. And this is one figure that shows you really where the warming has occurred the most. This is a 25-year period from 1976 to 2000. A blue dot is cooling over that interval. A red dot is warming. A big dot is more warming or cooling. And a little dot is little change or no data. The graph is mostly red, obviously. It's not red evenly, is it? It's not nearly as red over the oceans as over the land. That's predictable from the basic physics. The oceans have a high heat capacity. It takes a lot of heat to warm them up. And ocean water circulates. Water dives back down. Land warms up more quickly when you're in the interior of a continent, in a place like Missoula. Colder in winter, warmer in summer. So we see more warming over land than over the oceans. More warming at northern latitudes. The most warming at northern latitudes. Again, predictable based on first principles from feedbacks with things like snow and ice. If you melt snow and ice and uncover water or ground or plants, you soak up a lot more of that sunlight and heat. So if you want to go to a place right now that's warmed the most, in many cases by 5 degrees or more, that's the place to go. So where you see those big red dots, that's about a 4-degree Fahrenheit warming over this time interval. Okay, another tipping point. Sea ice, in this case the North Pole. Many of you will have seen these kinds of data. This is a map. This is not a map, it's really an image, a satellite image, taken in 1979 in September, and the same image taken in September in 2005. So where are we? Well, here's Alaska here, Kamchatka, Russia here, Greenland is here, covered in snow and ice. Okay, why September? This is the period of the year when the ice cover is the smallest. So summer comes along, that ice shrinks. And then winter starts coming back in, the days shorten, go to complete darkness, that ice builds back up. So this is the sort of the smallest size. Why 1979? This is the year that a satellite was launched. It's not a year that was cherry-picked because the ice was particularly small or anything. In fact, this trend goes back well before 1979. So what you see in 2005 is something interesting, not just from an environmental standpoint, but from a geopolitical standpoint. You see the coast of Russia being ice-free. You see the ability to move a ship essentially through this region ice-free, something that's been desirable for a long time. And you see, most importantly in the context of this discussion, a huge swath of that ice missing. So about 20% of that ice disappeared compared to about 30 years earlier, 25 years earlier. So that was 2005. a large report came out that year that talked about long-term trends, the possibility of long-term melting of the North Pole. No real discussion of anything happened very abruptly or very quickly. And then 2007 came along, and that's what the ice looked like. Now all of a sudden, we had 50% of that ice loss in this case. Here's the trend line of the sea ice. Here's the 2007 data. So zero's down at about here. There's been about a 50% reduction to this point. 2008, 2009, and 2010 have not quite come to the 2007 level, but are all down here. Trust me, sometime in the next few years, the number will be less than 2007. And the very real possibility, maybe even in my lifetime, quite possibly in the lifetime of some of the students, the North Pole will be ice-free in summer. If you're a walrus, a seal, a polar bear, that has enormous consequences for you, for your reproduction. Some of you probably saw there was a story that came out literally today that a radio-collared polar bear had swam 9 days continuously. Did you see that? 425 miles to get the sea ice so that it could feed. Its cub that was with it didn't make it because the distance was too long. Okay, so a very real possibility that consistently in summertime, the North Pole will be ice-free. I wrote an op-ed once about Santa Claus and the consequences of that, but I'll spare you. Santa had to move, let's put it that way. Okay, now we're moving from real data to projections. And now there's no real world. These are climate model based. Nobody knows exactly what's going to happen. But when you look at a consensus from the different climate models that now project for sort of a middle-of-the-road scenario for fossil fuel emissions, the number of people on the planet, you see a picture that looks like this. Approximately the end of this century, more warming over land than over oceans, just like we've already seen. More warming at the northern latitudes, where you're looking at purple up there, you're looking at 10 degrees Fahrenheit, approximately. Absolutely massive changes. We'll talk about some possible tipping points associated with that warming because there's lots of carbon stored in permafrost, for instance, in those northern latitudes. There's more carbon in permafrost up here than all the carbon we have in our atmosphere currently. So if you liberate that carbon, our job to stabilize concentrations becomes a lot harder. Okay, less warming over the oceans, less warming in the tropics. So when we think about, another take-home message, I guess, when somebody tells you that the mean annual warming is going to be 2 or 3 degrees C, perhaps, 3 to 5 degrees Fahrenheit, don't forget that that's not representative of what's going to happen on land, and it's not representative of what's going to happen in everywhere, and especially at the northern latitudes. And in some places, it'll probably be less. Okay, another projection. My home state, the state of North Carolina. This is work from a couple of colleagues, Norm Christensen. Here is, based on digital elevation maps at least, a picture of what might happen to North Carolina in a realistic scenario for this century. So open water here in blue, land in gray. Here are the Outer Banks. Hatteras, one of the most beautiful places on the planet as far as I'm concerned. Dark blue, a 1 foot level increase in sea level. Royal blue, we'll call this Duke blue, Carolina blue, if you'll indulge me. 1 meter rise, 3-4 foot rise. Not likely this century, but possible if you've been following the literature for Greenland, for instance. The Greenland melt is happening much, much faster than anybody predicted, even 5 or 10 years ago. But look what happens. All right, there's a large coastal area that goes underwater. Most of the Outer Banks goes underwater. Right, there are a few places that are left. Now, left to itself, nature's pretty resilient. So what would happen in a normal world? Okay, the Outer Banks wouldn't disappear. They'd move, right, from a geomorphological standpoint. But we don't want them to move. Right, we've already spent billions of dollars to try and stabilize them, to protect the homes that we already have built there, and the towns that are there, and the roads that are there, and everything else that we have in place, the infrastructure that we have, that we're going to spend more and more billions of dollars to try and keep in the same place, and our job's going to get harder and harder and harder as sea level rises. Okay, some other things to think about, and then we'll move into sort of the conservation perspective. I just want to spend a few minutes talking about timescales, because 2050 and 2100 seem like a long time. Now, 2050 Doesn't seem as long to me now as it might have when I was in college, only 40 years from now. But here's a scenario of what happens if we stabilize carbon dioxide. Not if, but when we stabilize. At some point we will. So let's look at today. Now we're going out 100 years here, 1,000 years here. So let's go through a trajectory, a series of things that happens. So at some point, the emissions of carbon dioxide from the planet peak, and then they start to go back down. Okay, carbon dioxide itself takes longer to stabilize. Here's the stabilization trajectory for carbon dioxide. There's a lot of equilibrium for the carbon dioxide to come into equilibrium with the oceans and land and plants and soils and all of that. Temperature, even after CO2 emissions start to drop, goes up for another couple centuries at least. Sea level rise, ice melting, thermal expansion of the oceans. Very little uncertainty with this term. This is a benchtop experiment that you probably did in high school. You heat water up, that water expands. Quite predictable. This one, less predictable. So once we fix the problem, 1,000 years of sea level rise, at least 30 generations of people dealing with it. Many of our major cities underwater. 20 feet of water in Greenland, does all that water go or not? Nobody knows completely. Another couple 100 feet on Antarctica. So I just want you to think about the timescales of not doing something about this. Okay, the theme of the talk was tipping points and conservation. Here are some physical tipping points, and we'll get to some biological ones. So what are some things that keep me up at night when I study climate change or the environment? Here are a few. Some of them more likely, some of them less likely. The one that really keeps me up is the one I already mentioned, and that's the permafrost term. So there's well more carbon in this permafrost, most of it at northern latitudes, a substantial stock in tropical peatlands. Some of you may remember that there was a El Nino year and a fire in 1997, 1998. Dried that tropical peatland out, it burned, liberated 1 billion tons of carbon dioxide to the atmosphere in 1 year because of the warm temperatures and drying. No way to attribute that to climate change necessarily, so I'm not saying that. But there's large pools of carbon that are there. This is the one, the northern one is the one that worries me for the reasons that I showed you before. That's where the warming is going to occur. And if you lower that permafrost depth, there are enormous pools of carbon that are then that can dry out, can be decomposed by microbes. There may be some counterbalancing factors. You're probably going to get some additional tree growth and other things that will put carbon back into that system. So it's not a simple answer. But long term, this one keeps me up at night. Rapid changes in ice sheet threshold. This is a piece of ice about the size of Rhode Island that capped off from Antarctica about 2002. So a lot of uncertainty about how quickly the ice will go. I should say that I talked before about the North Pole melting. The North Pole is like an ice cube in your Coke. That buoyancy has already been taken into account, so we can freeze that or melt that. It does not affect sea ice. But when you have ice over Antarctica, or you have ice over Greenland, and you melt that ice, it raises sea level. So Greenland, I would argue, more than Antarctica, is the most vulnerable pool of ice on the planet. 20 feet, as I've said. It's not enough just to think about the melting. We've got to think about rates of snowfall and water into the system as well. But that one keeps me up a bit too. Methane clathrates. This is essentially a frozen mixture of methane and ice, the bottom of continental shelves and such. There's a huge pool of this. Methane, as you know, is a much more potent greenhouse gas than carbon dioxide is. Not likely to liberate anytime soon. In fact, I would argue that the issue here is more, will we use this as an energy source before it melts from a climate change standpoint? Okay, so three areas of pretty large potential changes. Let's talk about some biology then. Let's talk about some biological tipping points. This is one that is relevant to you here in Missoula, I believe. You have mountain pine beetle outbreaks that have been happening all over the western U.S. Here's the British Columbia example. What you're looking at here is a map of British Columbia. All this area that you see is an area that has been attacked by mountain pine beetle in the last 5 to 10 years, and especially in the last 3 to 5 years. Okay, why do people think that this is a climate change issue? Well, they think that this is a climate change issue because what knocks this beetle back in eggs and larval form is winter temperatures. And if you don't get the winter temperature below that threshold of about minus 35 or minus 40 C, then it overwinters successfully and it's ready to go come spring. There's some projections that this particular species could go all the way across to the eastern part of Canada too. Large influences on timber availability, large influences on the carbon balance because there's a tremendous amount of carbon stored in the trees of those forests. So it's an example, really, of the kind of interaction that we might not have predicted. Let's talk about another one. Let's talk about ocean acidification, one of the most insidious problems, I believe. So what is this ocean acidification? Well, for those of you who haven't heard about this is carbon dioxide that goes into the atmosphere from fossil fuel burning or land use change, and that carbon dioxide dissolves into the ocean water. When it dissolves into the ocean water, it forms carbonic acid here. That carbonic acid then breaks down into bicarbonate, and then here, also carbonate. All right, so this is not a chemistry class. Why is this important? Well, this species, carbonate, is what reef-building organisms use, many phytoplankton. This is this chemical species that the base of the food chain and a number of organisms in the ocean use to form their skeletons. Okay, and when you would think, at least I would think on first principles, if you load the oceans with carbon dioxide, there's going to be more carbonate available. But that's not what happens. What happens is you shift the abundance, the relative abundance between this bicarbonate species and carbonate, so that the carbonate from here and the acidity from here come together and form bicarbonate and lower the concentration of carbonate in the ocean water. So far we've reduced the pH of the oceans about 1/10 of a pH unit. That's a log 10 scale, so that's about a 30% reduction. And we're projected to reduce the pH by maybe 0.3, 0.4 units more in this century. And continuing. What happened? Okay, a little more chemistry. This is just a figure showing you essentially the change in relative distribution. So on the x-axis here we have pH. The green bar at the top shows you where we are today in terms of pH. Carbon dioxide in the atmosphere drives the pH this way. Here is carbon dioxide concentrations. So essentially what happens is as you drive this system, the oceans, to a more acidic system, the amount of carbonate in it drops, the amount of bicarbonate in it rises. Some biology. This is an experiment that was done, not my work. Essentially what you're looking at here is a coccolithophore, a phytoplankton species that's growing in an atmosphere similar to about 300 parts per million, close to a pre-industrial concentration, and about 800 parts per million, sort of at the top or just above the top of that figure we looked at. What you see essentially in this graph, this figure, is this image, is the skeletons, the shells, essentially starting to dissolve. And you see kind of the furry, the fuzzy edges there. So this is a species that's sort of fighting that equilibrium, that carbonate-bicarbonate equilibrium. Now there's almost no uncertainty in the fact that the oceans will become more acidic. There's a tremendous amount of uncertainty into the ecology of how different species will respond in the oceans and such. But this is something that is, there's no uncertainty about temperature or rainfall or anything else. This is a direct result of loading the system with carbon dioxide. This is a figure from a paper a couple of years ago, really highlighting work that it's more than just the carbonate concentration, that the temperature also influences the ability of species to succeed. So what you're looking at here is a trajectory of concentrations of carbonate and the Earth's temperature in the glacial to interglacial period, and then sort of where we're driving the system through climate change today and fossil fuel emissions. So we're forcing this system and forcing these species into regions, state space if you will, that they've either never seen before or haven't seen for millions of years in a lot of these cases. And for that reason, we really don't know a lot about what's going to happen in those cases. It's hard for us to predict how this will affect the base of the food chain, the trophic levels and interactions that these depend on. So driving a system somewhere that it has either never been, or in this case hasn't been for a very, very long time. Okay, let's talk about extinctions. As you all know, the Earth has been through 5 major extinction events, the greatest being the Permian extinction. On the y-axis here we have the percentage of families that went extinct during that interval. The x-axis is time, with the years that are gone. Here's the Cretaceous, of course, the last great extinction that drove the dinosaurs extinct and led to the rise of the mammals. So an important question that many people work on is, are we creating a sixth great mass extinction today? There are many people who believe that we are. If you were a geologist and looked at what happened so far, you would not see this kind of mass extinction peak, so I don't think we can say that that's the case yet, in my opinion. But through all these factors and many other things that are driving pressures on the Earth, land use change, different sources of pollution and such, exploitation of species. This is a really important question. Are we driving the Earth system to something that only sees every 50 or 100 million years in terms of loss of species? Okay, from a climate change perspective, of course, there are a lot of people working on how long it takes species to move. So, for instance, will species be able to keep up with the pace of temperature change that I showed you before? This is one model simulation. This is based on a Hadley model from the British Climate Office, 2100 simulation. I think it's a 3 degrees centigrade increase. I wouldn't put a lot of stock into the particular colors that you see here. So what are the colors? You see today in 2100 here, loblolly pine is the blue up there. That's the most important plantation species in the southeast where I live. You see most of that loblolly habitat moving out. You see sugar maple and other things moving up into Canada. I think there's a lot of reasons not to. The point of this slide isn't to say this is what the world's going to look like. The point of this slide is to show you that things are going to move, and some species are more or less capable to keep up with that movement. So what about the ones that can't keep up? All right, what about the ones that might be able to keep up? If you're a bird, you can fly. If you're a tree, you can't. Maybe you're a tree with wing seeds, that they'll move a lot. Maybe you're a plant whose seeds are carried by insects and you'll move. But there's an increasing number of people trying to think about under what conditions do we move things intentionally? Or maybe put it differently, think about a species that's restricted to certain conservation reserves and it needs to move and it's got to jump hundreds of miles perhaps. Or maybe there's no reserve for it with suitable habitat. So what do we do in these cases? Do we do what's called assisted migration? Do we consciously pick species up and move them 100 miles to the north or south? 500 miles to the north or south? Under what conditions do we do that? Who decides if we do that? When do you do that? Not everybody waits for scientists like me to go to meetings and take our time and work through these problems. Some people just do it. So here's a case where a group of people got together and simply moved the species. This is one of the rarest trees in the world. This is Torreyana. This is a species of less than 1,000 individuals restricted to a very narrow corner of upper Florida and southern Georgia. So these people took matters into their own hands. So this would be equivalent to leaving this meeting and saying, I got to do something. So we go to the bar. Not that any of you undergraduates would go to the bar with me, but indulge me, if you will. We go to the bar and we say, we got to do something about this. So 10 of us get together and say, we're going to move this. We're going to pick this species up. And they moved it 1,000 miles to North Carolina and a couple of other places. Okay, unilaterally. That's a bad decision in my opinion, but that's not a decision that you can necessarily stop. Okay, driven by a concern for a species and driven by frustration with the Endangered Species Act, with a lack of action on climate change. Is that the right thing to do? Probably not. Okay, here's an even crazier idea. Some of you know about this, rewilding of North America. So you all know that we have many species that went extinct in the sort of 10 to 20,000 years ago time frame. Here's a proposal from a few folks who said there's all this essentially unfilled niches in North America and rangelands and such. We have all these species that are in trouble in Africa. Why don't we just recreate the Pleistocene megafauna from an ecological niche perspective in North America? So let's move cheetahs and lions and giraffes and things over here. So I don't think I have to say anything more. I think this is a terrible idea also, for many reasons. Too many reasons that from ethics to ecology, too many reasons to go into. But this is what happens when we start thinking about a world where everything's out of whack. You have to think about managing more and more things. So let's manage not one species, let's manage 1 million species. Now our job is to keep track of 1 million species like God and move things around and make sure they're all in balance, and guess what? We won't do it. It won't work. Now this one's more interesting. Some of you saw this a couple of weeks ago, right? This is going to happen. I promise you this will be successful eventually. This is a project that was announced 10 years ago, a couple of weeks ago, to a 10-year time frame, Japanese and Russian scientists, to bring the mammoth back. All right, so why is this going to work, in my opinion? This will work because you have frozen tissue. There are mammals that have been frozen. The proposal and the approach is to take a nucleus out of that mammoth, insert it into a surrogate mother of an elephant, and have the elephant bear that mammoth. Yeah, so we could talk about that for a while at the bar, huh? Fascinating idea. So in the basement of Duke University, when I teach extinctions, I take the students down to the basement, we open up some cabinets, and I hold in my hand for them a sample of the passenger pigeon and the Carolina parakeet, two birds that went extinct about a century ago. The Carolina parakeet is an exquisite bird. So if somebody gave me $5 or $10 million, I might think about it. And so what are the rules here? Okay, who decides? Is it driven by technology? Is it just a technological issue? If we can do it, we'll do it. Is Michael Crichton right? Is it going to be Jurassic Park? This is coming, and the technology is going to grow, and we're going to have to answer these questions from not just an ecological standpoint, but an ethical standpoint too. What are the rules? Who decides? Now, speaking of rules and who decides, one more example before we talk about solutions, geoengineering. So what is geoengineering? Geoengineering is the large-scale engineering of the environment, essentially the direct manipulation of the Earth's climate to combat or counteract the effects of climate change. So why in the world would we do this? So the reason this is at least being discussed is because an increasing number of people look at the inaction on mitigation or on reducing fossil fuel emissions, or say, what if things really start to spin out of control? What if that permafrost carbon starts vomiting to the atmosphere? What if all these things happen? What do we do? Or can we do anything? So nobody promotes this in the absence of reducing emissions and increasing efficiency. We should never talk about these kinds of approaches without having that discussion. But this is science fiction. So some of you, how many of you read Dune for you undergraduates? Have you ever read Dune? This is Dune. This is terraforming. I testified in Congress last year about this. Your representatives and your senators are thinking about research in this topic. Okay, two flavors for engineering, geoengineering: removing carbon from the atmosphere, reflecting sunlight. Really very unfortunate that these two things are linked under one term. So we really need to fix that in a sense. This is, how can we reflect a little bit of sunlight back out into space to cool the Earth? Okay, so if we don't fix the emissions problem, well, let's try and tweak the temperature dial a little bit. Talk about that in a minute. That's a happy thought. Here's removing carbon. So we can talk about efficiency, we can talk about reducing emissions, but we have no way to actually take the carbon dioxide that's in the atmosphere out if it causes a problem unless we use plants or unless we develop new industrial methods to scrub that carbon dioxide from the atmosphere. That's what carbon dioxide removal is all about. So are there industrial processes or biological processes that allow us to take that carbon out of the atmosphere, store it deep underground, something I work on, or conceivably, less preferably in my opinion, into the oceans, for instance, or somewhere else. So let's go through a couple of examples of these. Okay, why in the world would anybody do this, and why do we think it would work? Okay, the best example is volcanic eruptions. So in 1991, Pinatubo erupted. It injected 10 to 20 million tons of sulfur dioxide up into the lower stratosphere, so high into the atmosphere. That's important because then the particles stay up there and they circulate all around the Earth. The Earth cooled by 1 degree Fahrenheit for over a year, attributable to that eruption. So that's the fundamental idea, is essentially using aerosol particles to reflect sunlight. Now, other things happened when Pinatubo erupted. We had a global drought. So why is that predictable? Well, so every time you tune the dial down for sunlight, let's say you had the ability to do that, you're going to tune the dial down for water a little bit more, because water responds more to sunlight than temperature does. So anytime we want to think about changing sunlight, we're going to think about changing precipitation more. People have done simulations that if we blast stuff into the stratosphere, we have the potential at least to fiddle with the recovery of the ozone hole, to delay the ozone hole recovery by 50 or 100 years, to cause increased ozone loss over the Arctic. Maybe we can engineer a particle that doesn't do that. Maybe we can't. Maybe we think we engineer a particle that doesn't do it. We blast it in the stratosphere and it causes a problem, but then they all drop out in a year. So, it's only mildly catastrophic. It's at least based on first principles. Okay? I'm not advocating this, but people are thinking about this because of a lack of action. Space mirrors. Great idea. The gravity equal point between space and the Earth. We put a bunch of things out there. Yeah, fine, fabulous, but we don't have the money to do it and the technology, and maybe in 50 or 100 years and I'll be dead. So let's skip that one. Artificial cloud cover, an albedo. Feasible, possibly. Not clear that it'll work. So imagine a fleet of ships that sprays salt water up into the atmosphere. Those salt particles form cloud nuclei. There are regions of the oceans that are dust limited, nuclei limited. So you get those into the air, you form clouds, you reflect sunlight, locally in this case. But maybe locally over a scale of 1,000 square kilometers, different places. You're fiddling with the energy balance. You're trying to get some of that sunlight back up and out of the atmosphere. You're cloud covering the oceans. You're influencing primary productivity, phytoplankton. You're reducing evaporation in these systems. So all of these are imperfect. They all have lots of other consequences, but people are thinking about them. Carbon removal technology is one that you will have heard of, ocean fertilization. So there are large regions of the Earth's oceans that are iron limited. The notion is that you can sprinkle iron, essentially bleed very small amounts of iron in the ocean and get a phytoplankton bloom. This is sort of analogous to fertilizing land plants, if you will. And if it worked in a perfect world, you'd get that phytoplankton bloom, those organisms would die and they'd sink down into the deep ocean in the sediments, and you'd get rid of that carbon dioxide. A number of experiments have tried this really before people were thinking about it from a geoengineering perspective. It works consistently to get a phytoplankton bloom. It does not work consistently to get that carbon down into the deep ocean because grazers come along and eat the phytoplankton. Sometimes the iron breaks up in the water. So this one I think is probably not going anywhere because really what we're talking about doing is eutrofying the oceans. This is analogous to eutrophication of freshwater lakes. You get an algal bloom effectively, and then that drops down. There are issues with hypoxia and all kinds of things. But under discussion. There are commercial companies trying to get permission to do this already. Okay, some good things. CO2 removal, if you will, from land use management to protect sinks. Now you could say, well, this really isn't removing carbon dioxide from the atmosphere, but if you can keep carbon that's locked up in trees from going into the atmosphere, then you can make real headway. And this is part of the REDD effort, reduced emissions from deforestation and degradation. Lots of co-benefits here. Great idea. Good for the carbon balance, good for the water balance, good for biodiversity, additional biophysical cooling. So the issue here is we're not used to paying people for not doing things, right? That's what this is about. So I pay you not to do something. We have some experience with this in the country. The Conservation Reserve Program, 30 million acres of agricultural land in perennial covers and such that we pay people not to grow crops on to reduce erosion and such. So there's some experience in this. So you really are talking about a lot of money and a lot of other issues associated with this, but in principle, good idea. Not big enough to solve the problem, but big enough to make a dent because of that 1 billion tons a year we looked at before. Another good idea, possibly, crop brightening. So there's 1 billion acres of land on this planet that we use to grow food. If you could make those crops just a little bit brighter, and you only have to reduce sunlight by a couple of percent to offset the warming attributable to a doubling of carbon dioxide. You make those crops a little bit brighter, you can cool the earth a bit. Now, can you cool the earth without reducing primary production, without reducing yields of the crops? So I would argue that you're not going to get a benefit from brighter leaves, because if you got a benefit, we'd already be doing it. So that people are testing this sort of thing all the time. But there is a possible niche here, and that niche is that we don't We don't ask people like Monsanto and Syngenta to breed crops to have higher albedo but the same yield. That's not how they work. But that is something that an effort that the government could put in place if we wanted to, or at least wanted to think about that. And it might have some co-benefits. Those companies spend billions of dollars a year thinking about drought tolerance for crops, probably the largest area of plant breeding and bioengineering right now for global agriculture. This has the potential to help that because it cools the leaves a bit. You get rid of some of that sunlight. It reduces water loss. So at least worth thinking about. But large-scale manipulations, if you're not doing this sort of thing over tens to hundreds of millions of acres, it's not enough to make a difference. Okay, a terrible idea. Couple of proposals. Great for a thought exercise. The deserts are, nobody likes the deserts. I do personally, but I'm an environmental nerd. So model A, let's make the deserts reflective. So instead of trying to increase the reflectivity of the whole planet, let's just take a few areas and sacrifice them. So we're going to cover the deserts with an aluminum film. That 3 watts per meter squared savings is enough to offset essentially all fossil fuel emissions. Costs a couple trillions a year. Or even better, let's take the Australian deserts and especially the Sahara. Let's use a lot of energy to desalinate water from the oceans. Let's truck it thousands of kilometers into the center of the continent. And let's plant a forest that's almost doomed to failure at the meager cost of a few trillion per year. I don't even know where to start with how terrible this idea is. In case I think you've gotten that idea now, so let's move on. There are good ideas out there. There are bad ideas out there. Interesting thought exercise, terrible in practice. So what are some good ideas, just to finish up? Renewables, obviously. So Montana has a pretty aggressive renewable electricity or renewable portfolio standard. 15% of your power by the year 2015 is to come from renewables. That's admirable. More aggressive than my home state, although my home state was the first in the conservative southeast to adopt a similar standard. Okay, concentrated solar, tide power, wind, photovoltaics. Clearly these are real opportunities. So I like to use Denmark as an example that some of you know. Denmark made a decision as a society to invest heavily in wind power. They now generate more than 20% of their electricity with wind. They're in fact the world leader in production associated with wind turbines, a market that's worth billions of dollars a year, and tens of thousands of jobs per year. So the fact that we haven't invested in this field as a society in the way that countries like Denmark have, has left us behind, not just environmentally, but economically too. So we could have chosen to do these sorts of things. Photovoltaics are another. We developed much of the photovoltaic technology that's in use in the world. Much of the production, however, is in China and elsewhere. Great idea, obviously. Another great idea, efficiency, whether it's homes, cars, whatever you want. So my favorite example, 1908, Henry Ford rolls off the Model T from the assembly line and gets about 20 miles to the gallon. Okay, so what's the fleet mileage today? It's about 20 miles to the gallon. Now our cars do better things. I can listen to CD. I've got air conditioning. But fundamentally, we really haven't made any headway in terms of overall mileage. But clearly, there are lots of cars today that can get 50 miles to the gallon. Here's an area where you could cut 10% of our total fossil fuel emissions by asking people not to change their behavior one bit, just to change the cars that we drive through time. And this is, of course, the idea behind increasing the CAFE standards and such. But you've got hybrid technology. You've got electric cars like the Nissan Leaf and the Chevy Volt. Does anybody have a Leaf or a Volt in this room? I'm not sure they're available here yet. They're not available where we are. Electric cars, great idea. If your electricity comes from hydro, maybe. If it comes from coal, sort of a wash, right? So it matters a lot where your power comes from. Don't buy into the argument that just because a marketer is telling you it's an electric car, it has zero emissions. Not so. Efficiency. What's the consequence of our increasing reliance on fossil fuels? Well, I would argue that these are the kinds of consequences that we face. Mountaintop mining. If you've ever driven through Western Virginia or West Virginia, parts of Kentucky, this is an ugly way to get our coal. This is literally knocking 500 feet off of our mountains and making them flat so that we can have access to material. Now, I have no idea. It doesn't happen in Montana because we don't have the technology to do this at 12, 13, or 14,000 feet. But someday there will. And someday there'll be something valuable enough to do that here. And I have no idea whether there's a law in Montana against mountaintop mining, but if there isn't, my challenge for you tonight is for somebody to walk out this room and make sure that there is before it's a decision of a project and jobs versus your mountaintop. Fix it now if it isn't already fixed. And take it off the table. Tar sands, another nasty way. Very energy, what I mean by nasty, what I mean is disruptive, extremely energy intensive to get those particles of oil to coalesce and flow out of the materials. Rick Bass is in the audience, just had a book come out on this. I have not read it yet, but I would encourage you to. Shale gas, something I work on individually in our group. Lots of advantages to natural gas, much smaller carbon footprint than coal, for instance, much cleaner. There's no mercury and other things. Problem with shale gas extraction is that each time we produce a well of shale gas, right now we're putting about 3 to 5 million gallons of fracking fluid underground, and that fracking fluid is relatively unregulated, and only about half of it comes back up. So this long term is probably a good thing, in my opinion, except perhaps for the break on energy prices and the perhaps slowing down the adoption of renewables. But we have some things to work out in terms of water and regulation there. Again, my personal opinion. There are opportunities for land-based sequestration, something I work on. This was the first experiment in the world to grow a forest at a high CO2 situation. This is at Duke University. So for the last 15 years, we've been growing a pine forest at ambient carbon dioxide concentrations and almost 600 parts per million carbon dioxide, and looking at changes in growth and water use and things like that. So we can manage our forests, at least the plantations, through increased density and rotation length and things like that. We can store carbon underground in principle. Carbon capture and storage, something else I work on. So imagine a coal plant or a cement facility or something here. There are strata underground that in principle hold carbon dioxide if you pump it there. Gas and other things stay underground for millions of years. Lots of issues here with it staying underground. The biggest issue here, in my opinion, is cost. So I think in principle this works. You can argue whether prolonging the life of coal is a good thing or a bad thing. I believe in the 50 to 100 year time frame we need this. I hope this works. If this doesn't work, we are in trouble because a large part of the world is using coal, is building coal plants now, and those coal plants are going to be on the ground for 40 or 50 years with no ability to retrofit them or do anything else. So a tremendous amount of work being done in this area today. Right now, it's just simply too expensive to be economically feasible. Okay, now how about just finishing up the many benefits. So we've gone through some scenarios, many of them sort of wild. They're really given a talk like this with all these sort of strange scenarios in them. But how about let's bring it back down to earth. What are some of the benefits of fixing the climate change problem in addition to climate change and species and such? Well, here are a few of them. In the US, coal-fired power and car exhaust produce the 6 things we spend billions of dollars a year to regulate and to reduce emissions of. Ozone, particulates, nitrogen, sulfur dioxides, lead. 2003, the blackout in the Northeast came when the Northeast literally went dark, the kind of experiment people like me would love to do, but for some reason they don't let us. Visibility improved by 25 miles when the power grid went off. Smog and ozone dropped by half. Gases contributing to haze and acid rain dropped by 90%. That's a pretty amazing experiment. Urban ozone formation, strongly correlated with temperature. Summer extreme temperatures go up with climate change. Ozone alert days, ozone issues are going to go up. All of these things influence tens of thousands of people's lives, kill tens of thousands of people collectively through our energy, and we accept that risk. You fix the climate change problem, you go a long way to fixing these kinds of problems too. So that's maybe one message in terms of solutions that I'd like you to leave you with, is to think about taking climate change out of an isolated box and thinking about all the things that it would help us to do something about. The environment, human health, balance of trade for the oil we import, national security, water and air quality. Pick whatever list you want. Democrat, Republican, I don't care. Hey, pick your local passion. So I'll finish this. Pick something, especially for the students in the room, pick something to get excited about. Okay, save a river, change your school, get rid of your car. My wife and I, our family, we think a lot about food, so we try and produce as much of our food as possible. Dairy goats, chickens, mushroom logs, hunting, fishing, nothing new for people in Montana. This is just one of our passions. One way to reduce our carbon footprint. By no means does what we do here offset all the carbon dioxide emissions that I generate. I would in no way say that. But pick something that interests you, change your life, change the people around you that you care about. Finally, as Corey mentioned, I published this book about 7 or 8 years ago. I've got a couple of quotes and comics up here. So here's one that's about almost 10 years old now. This is a Roz Chast cartoon from The New Yorker. 2000, the millennium, how to deal with the upcoming recession, inflation, depression, ice age, greenhouse effect, energy crunch, population explosion, and complete end of the world in the year 2000. And one of my favorite authors, Robertson Davies, a Canadian author, Marchbanks, the world was scheduled to end today, but something must have gone wrong. We face a lot of choices. We can do something about this problem. And I hope if you remember any one thing from the talk tonight, it's that those solutions are feasible, they're in that grasp, and if we don't take those steps, all the kinds of things that I've been talking about up here are possible, and that's not a world that I want. Thank you very much. So we should have plenty of time for questions. I was told the students aren't allowed to leave, but that doesn't keep other people from leaving. Can't blame them, really. Any questions? So for TV, do you want to give people a mic, or do you want me to, I'll repeat the questions.
You talked a lot about what's going on with climate, and you talked a lot about corporate solutions. Can you talk a little bit about local solutions? What can we do? What can I do?
Yeah, so I guess in that last slide, when I was talking about food, I had local in mind, but I often finish with a local slide. So I think obvious things are lighting. You know, in the short term, get up and turn your thermostat down a few degrees. Longer term, live closer to work. Ride a bike. Insulate your homes. None of these things fix the whole problem, but all of them take discrete steps to fixing that problem. So I think what we need is a mix of local solutions. I do genuinely believe that this is a problem that will be solved not just at the local level, however. The problem is too big. It's going to take state, national, and international activities, but everything starts locally.
You've well defined the threat. Can you, or is there any projections for what the risk is if technologies and human population growth do not change significantly over time? What is the risk of human extinction?
So for those of you who couldn't hear, the question is about what if we do nothing? Is there, at what point is there a risk of human extinction? So I don't personally believe that human extinction is likely anytime soon. Have any of you ever seen the Gary Larson cartoon with the dinosaurs? There's a dinosaur up at the lecture podium like I am and saying, the world's climate is changing, blah, blah, blah. We all have a brain the size of a peanut or something, but there's all this sort of optimism that nothing's going to happen. So I sound a little bit like that. I'll tell you what I worry about. I worry about disruption. Refugees, disruption. I worry more about, I think relatively wealthy countries like the US are going to be in much better position to deal with this than someone living in Bangladesh, where the storm surge, the floods. What I really worry about are the millions of other species that are going to be left behind. So I care about people first and foremost, but there's nobody looking out for that world and all those other species. I don't want that sixth peak there that, of all the legacies, climate change is a long-term problem, but no legacy is longer than extinction. So I believe the human species is resilient. The question is, what kind of world do we want and do we value?
On that slide you had that showed the peaking of fossil fuel consumption and then the ice in terms of years and time frame. What I was curious, what makes you say that eventually we will cap our emissions or bring down our emissions? I was curious why it is that we will, as opposed to some other natural process.
So I think the question is, the question referred to that figure I showed you of the time course sort of going out 100 years and 1,000 years. And the question is, why do I think at some point we will actually cap carbon dioxide emissions? Well, because they can't go up forever. At a 1.5–2% per year, that's a doubling time of, say 30, 40 years or so. Things spin out of control in not very many centuries. So, maybe it's not 50 years, maybe it's 150 years, but that number has to come down at some point. I hope it comes down sooner than later, personally. But I'm not sure I understand your question, to be quite honest. But do you want to give me one more try?
I guess I was getting more at maybe I misunderstood what you were saying, but it sounded like you were saying that we would make the effort to bring it down eventually, as opposed to, say, running out of.
Okay, I see. All right. So the question is, why not? What happens if we just sort of burn it all up? We don't want to go there. I mean, just point blank. I mean, there are, hundreds, thousands of millions, hundreds or thousands of parts per million of coal and stuff. There is way more carbon dioxide in coal and other reserves around the planet than than we want going up there. I mean, we would have runaway climate change if we burned all the coal and other things that are out there. We cannot go there.
I've heard a lot about the availability of fresh water becoming a problem. Could you talk a little bit about how climate change might affect the availability of fresh water in the world, or some possible solutions to that?
Yeah, so the question is about water availability and interaction between climate and water availability. First of all, I'd spent a lot of work professionally, obviously, on climate change, but I'd be quite happy for the climate change problem to go away. And one of the other things I work on is water quality and quantity. I think you could argue that if you could do one thing today to save human lives, that one thing would be water, not climate change. That's not to say that I think one is relatively more important or less, but there are still 1 billion people on the planet who don't have access to fresh water and sanitary water. Okay, climate change and water. All right, what's likely to happen with climate change? So first of all, globally, warmer temperatures is going to accelerate the hydrologic cycle. Again, just based on first principles, warmer air, you're going to evaporate more water. That's not the end of the story, though. So probably at northern latitudes, you're going to have more rainfall, more moisture availability. Some places, like if you've ever seen projections for the southwestern United States, like the Colorado River Basin, you have a double whammy projected of reduced rainfall and much higher temperatures, especially summer temperatures. So the water picture is much more complicated than the temperature picture, much harder to predict. But in general, the suggestions are that through sort of the southern U.S. up to mid-latitudes, it's going to be drier. Net drier because warmer, even if you have a little more rain, you've got warmer temperatures and more evaporation. Very far northern latitudes, you're probably going to have more moisture available, in part because when you get rid of snow and ice, ice in particular that's been over water, then that water is available to be evaporated to the atmosphere and rained out. I actually personally think, I'll finish, I think the effects of climate change on water availability and drying and soil moisture are more important from an ecological standpoint than the direct effects of temperature are. Maybe in the blacks and halfway to the back there.
Yeah, I have a question about if you come across behavior changes when we have increased efficiency in technology. I think it's called Jevons conundrum. They use the example of people driving a Prius and they just drive more, and so.
Yeah. So some of you saw David Owen's article in the New Yorker in December. Fascinating. So here's the premise. There's this 1850s or so, and I may get it wrong by a decade or two. This guy made the suggestion, looking at coal use in Britain, I believe, that when you look at a macro scale, increases in energy efficiency don't lead to less energy use. Right? And it's an aspect of that that's intuitive. So I think that's relevant. I think most of the economists, and I've read a lot of blogs, I actually spent quite a bit of time looking into this because it really calls into question one of the pillars of our approaches. Most of the economists believe that essentially what you get from the Jevons effect is a discount. In other words, that you really don't get full credit for that increased efficiency. And why don't you get full credit? So if I produce a vehicle that's twice as efficient and cheaper to use, more people are going to have access to vehicles who didn't have access to vehicles before, perhaps in India or somewhere else. So my use is going to go down unless I choose to drive more because I pay less. The cost of driving is more, but a lot of people are going to have access to that technology who didn't before. And he uses examples like refrigeration and other things to show every time we've made these things more efficient, we've reduced the energy use per unit, but we've increased the number of units. So I don't know what the answer to that is, but I gave you the answer the economists give. It's a great question. One back here.
What's the best method that you found, if there's a method at all, for persuading skeptics and extreme cynics that there is actually a problem and that this is created by conservationists to gain money from the government? Like, is it possible?
Like me. I think the most discouraging thing, so the last 6 months, if you're a climate change scientist like I am, the last 6 months have been pretty discouraging. So we came pretty close to a cap and trade bill. That bill, like our health care bill, I would argue, was an imperfect bill. It was large, it was complicated, but it was a start. And that fell apart at the last minute. Another fascinating New Yorker article, for those of you interested, talking about why that bill fell apart, and people like Lindsey Graham, the Republican senator who stuck his neck out, was hung out to dry, essentially, through that process. So in my opinion, the greatest mistake that's been made has been to politicize climate change. So that is what you essentially have become is if you're a Democrat, you believe in climate change, and if you're a Republican, perhaps you don't. Or if you're a Republican trying to get elected in a Republican primary, it's hard to say that you believe in climate change, even if you really do. So we've created a situation where we've essentially made parties polarized with issues that have no business. So when I teach in this for undergraduates, for instance, there's always a student in class who will get up and rail about the Republicans. Okay, so I voted for Republican presidents, I voted for Democratic presidents. What I always say to these students is, you may feel about that now, but when you look over the last 40 years, most of the major pieces of environmental legislation have been passed by Republican administrations. Clean Water and Air, President Bush, first President Bush, Framework Convention on Climate Change, Ronald Reagan supported the Montreal Protocol. So that's a long answer to your question, depoliticize it. Don't make it just about the environment. I really genuinely believe this is a problem that touches on human health, security, balance of trade, all those things that I gave you. I mean that sincerely. So get it out of that left-right radical box and let people see the benefits of fixing this problem. And I think that's how you reach people, environment, jobs, and the economy. Let's work in the back of our room for a minute.
Along with that, what has prevented really the awareness and really a lot of the misconceptions around global warming and climate change? What has prevented the public knowledge and really activism towards this issue?
So the question is, what's prevented perhaps more of a consensus on the topic? I'll give you my opinion, and this is my opinion now, not a scientific statement. I believe that the data are overwhelming. I study the Earth for a living. I mean, this is what I do. And I've already said, if I could do something else, I promise you I can get tons of grant money to do other things. I don't go out of business if the climate change problem goes away. I think in spite of this overwhelming set of data, and in spite of the details and the things that we don't know with 100% certainty, and there are a lot of them, I think it's fundamentally because we don't have a clear vision of what to do about it. And people have a hard time reconciling that these individual actions that we take can lead to this sort of global, this global problem. So I think, I used the ozone hole as an example, just absolute remarkable success within 2 years of the discovery of the ozone hole. So the ozone hole problem was fixed because of three things, in my opinion. The first, it had a sound scientific foundation behind it. So there had been decades of observations that went into it, and people understood the chemistry pretty well. Not well enough to predict the ozone hole as early as it came, but good science. Secondly, a direct link to human health through skin cancer. Okay, we don't have that in the same way. We have the sound science, I believe. We don't have such a direct link to human health with climate change the way we did for skin cancer. Thirdly, a relatively simple technological solution. So in the case of CFCs, we can switch to HCFCs and do other things. It's not that easy with climate change. At some point, we have to not just use or change the balance of the way we produce energy, we've got to reduce the amount of energy we use. So it's a much knottier problem. And I think, to be perfectly honest, it's hard for people to really come to grips with that. I would love to hear other people's opinions about that if we had a mic. That's a really good question. One more up here.
I just answered the question on the positive side of the whole thing. I've been frustrated by the government, especially with this sort of big rigs going down Highway 12, and you had said that you'd testified in Congress about geoengineering, and I was wondering kind of what the positives came out of that and what you thought, like doing these presentations and speaking to the government, and what's kind of come out of that. And you said some things about some of the research that you've done at Duke University and just kind of some things that will help drive us as students to do more and see more positive results, because I'm a little bit frustrated, I guess, with the government and not feeling like I have a voice. So for somebody that does have a voice, maybe.
Yeah. Well, I guess I'm naive enough in democracy to believe that the government responds ultimately to the priorities that we set. So in the case of in geoengineering, it was a really interesting. It was in the House. It was a really interesting session. Co-chaired Republican and Democrats. Thoughtful questions on both sides. A 15-minute diatribe about how greenhouse gases can't possibly affect the Earth's temperature because they're in low concentrations. It's all a conspiracy. That was a little less encouraging. But every person on that panel didn't take it sitting down. Every person on that panel, myself included, said that that's wrong and said why it's wrong. And sometimes I've answered some questions 100,000 times, and it drives me crazy to have to answer them 100,001. But I'll do it anyway. So there are some voices out there that just are not going to listen, period. And eventually those people are going to go away one way or another. I think the younger generation gets it. So I would say it's been a discouraging time because we came so close to a national bill. Don't give up and get involved. So vote the environment, get involved in the political process, and as we talked before, change the things, the people, the institutions around you. Eventually we're going to win. I'm an optimist.
A lot of it's always about money and the problems we have. What would you consider as some good ideas, some good ways to maybe give companies, corporations incentives to, do things that don't contribute to global climate change?
Yeah, so the question was about companies. What incentives can we provide companies to do the right thing? So I think I said this before. If you look, there are essentially three sectors of fossil fuel emissions in the United States. Our homes, heating and air conditioning and all of that, commercial buildings, and industry. And if you look at one sector that's made the greatest progress in efficiency over the last few decades, it's the commercial sector. Companies have thought for a long time about how to save, to be more efficient, to save money, partly because of commercial competitive pressures and such. Now that's not to say that there aren't some large-scale mega forces, from fossil fuel companies and other things that are, really have some issues with reducing fossil fuel consumption and such. But I actually think many people in the private sector, perhaps most people, get it. So we can provide incentives for them to conserve even more. But really in my opinion, we need to provide incentives for people like you and me to do more. We're the ones who really haven't changed behavior that much in terms of the energy use for our homes. Our homes are bigger now than they used to be, in terms of the amount of miles we drive and the kind of vehicles we drive. So utilities and lots of corporations are looking at ways not just to produce fuels in a more renewable, lower carbon way, but also to what's called demand side management, to get people to think about reducing use. And so instead of having to build a new plant, you provide financial incentives for people to use less energy and avoid that. So it is all about money. None of these things that I talked about, carbon capture and storage, none of those things are ever going to happen in the short term without incentives from the government. Okay, incentives that I think are useful for at least trying some things out. And that goes for wind and solar and things like that. That's why your renewable electricity standard in the state is so important.
So if you caught President Obama's State of the Union address a few days ago, he didn't make any mention of climate change at all. But he spent a lot of time talking about an energy innovation program or policy. And what do you think about the argument a lot of people are making now that putting a price tag on pollution is really not going to save the planet, that we have to put all our eggs into this massive investment, just like we did in the military or the internet, in thinking about energy innovation and pushing that one the hardest?
Yeah, that's a great question. So I have to confess, I stopped watching the States of the Unions a few years ago because they're so darn long. I do read the text, though, because I can read the text in about 5 minutes and do something else for an hour and 5 minutes. Going back to, especially to Bill Clinton, the master of long State of the Union addresses. So he didn't mention climate change. You're absolutely right. Now, frankly, that doesn't actually, I don't care. If you're talking about transforming the energy system, and that transformation of that energy system reduces fossil fuel emissions and improves the environment, then don't use the double C word. I don't have a problem with that. I mean, his mandate was pretty big, right? I can't remember the exact numbers, but it was something like 80% of energy by 2050. Always good to have a long date so that hardly anybody be around when that date actually gets here. But the spirit was there, right? Now his mandate was big, right? It wasn't just wind and solar and other things. It was discounted benefit for natural gas. I believe nuclear was in the mix. However you feel about nuclear, I think it ought to be in the mix, at least in the short term of 50 years. Clean coal was in the mix. As it ought to be if we can make it clean. We can't make it clean yet. So it was a pretty large mandate. It doesn't disturb me. The guy's a pragmatist. It doesn't disturb me that he didn't mention climate change. He at least mentioned energy. And I think the key message of that, in relation to the other discussion we had about the history of the climate change bill and such, is what will happen is we will not have a national bill in that sense. We're going to have a piecemeal approach, which may be better, may be more efficient through the energy bill, through the transportation bill, through the farm bill, and different pieces. Maybe that's a better way to go. I don't know. But right now, that's all we have, because we're not going to get a climate change bill in this Congress, certainly. Okay, one more in red.
You mentioned carbon sequestration and clean coal a couple of times and said that right now it's cost prohibitive, but that it's a necessary part of the solution. And I'm wondering if you can talk a little bit more about that and help us separate out the truth and the reality of the cost versus what some of us might hear as political rhetoric.
Okay, so the question being about carbon capture and storage. Carbon capture and storage, let's separate it, if you will, from, it's not just about coal. So another project we have in my lab, for instance, is waste to energy. So can you take municipal land waste, 2/3 of which is biological materials, plant material and such. Can you burn that for electricity and then store that underground? All right, so why is that important? Because there are very, very few ways we have to produce carbon negative results. That means there are very few ways we have to actually take carbon from the atmosphere and store it underground. Okay, so you can do that by using plants to take carbon out of the atmosphere and then to sequester that underground. Now, we don't go carbon negative by coupling CCS, carbon capture and storage technologies, to coal. We do have the potential, though, to keep those emissions, the large bulk of those emissions, from going to the atmosphere. The best estimates for cost are in the neighborhood of $150 a ton CO2, give or take $50. Okay, now that's not astronomical, but there are lots and lots of other things that are a lot cheaper than that. Some of you may have seen there was an article last week, a purported development in China for $30 a ton carbon dioxide for storage. Now, if you could safely store the emissions from a coal plant underground for $30 a ton CO2, by gosh, we've got something at that point. The response to that article from a number of people was essentially, everything's cheaper in China. It probably isn't a breakthrough, and it may not be real at all. So I don't know what the answer is. I don't have access to the actual numbers, but I believe the bucket for carbon capture and storage, the bucket is one of the few things we have where the bucket is big. And regardless of how you feel about coal, it's an approach that would really be great if it worked, just to get us over the hump of 50 to 100 years when we can phase coal out entirely. I guess that's how I feel about it. I hope that answered your question. Thank you for your